Here we are going to solve numerical on reheat Rankine cycle, which we have already solved theoretically using Cyclepad software. So we'll quickly have an overlook of the theoretical method. What is a reheat Rankine cycle? So there is a boiler, HP turbine, then reheater, then LP turbine, then condenser, pump. So if you see the cycle, we have 1 to 2 isentropic expansion in HP turbine, then 2 to 3 constant pressure reheating in the reheater, 3 to 4 isentropic expansion in LP turbine, 4 to 5 constant pressure heat rejection in condenser, 5 to 6 isentropic pumping, 6 to 1 constant pressure heat addition in boiler. Now we'll see the data. What is the given data over here? In a reheat cycle, steam at 500 degrees Celsius expands in HP turbine till it is saturated vapor dry. It means that point number 1 is superheated steam, then only point number 2 will be dry saturated vapor. So but in order to mark point number 1, we require two properties. Here only one property of temperature has been given. Next, it is reheated at constant pressure to 400 degrees Celsius. So it is reheated to 400 degrees Celsius, and then it expands in LP turbine to 40 degrees Celsius. So here you can see point number 4, temperature is 40 degrees Celsius. If the maximum moisture content at turbine exit is limited to 15%, so at point number 4, maximum moisture content is limited to 15%, means dryness fraction is 1 minus 0.15, that is 0.85. Now since we don't have any data about point number 5, we'll assume that point number 5, that is just water which is just entering before the pump, that point will be saturated liquid. So we have to find reheat pressure, that is this pressure of steam at inlet of HP turbine, that is this pressure, specific work output. Since here specific work output is given, we'll consider mass as 1 kg, cycle efficiency and steam rate. We have to assume all the processes are ideal process, meaning here we don't have to consider the efficiency of turbine. Here also we don't have to consider efficiency of turbine, and here we don't have to consider efficiency of pump. In the cycle all the processes are ideal, and we have to neglect feed pump work, means we have to neglect this work during the process 5 to 6. So how this is calculated is basically we first find the enthalpy of all the points 1, 2, 3, 4, 5, 6. Then what will be the turbine work? It will be H1 minus H2 plus H3 minus H4. What will be pump work? It will be H6 minus H5. What will be heat supplied in the total heat supplied? It will be heat supplied in boiler H1 minus H6 plus heat supplied in the reheater H3 minus H2. So all these things are done, and finally we can find efficiency, which is W net, WT minus WP divided by heat supplied QS. So we can get thermal efficiency. Now the same thing we can solve using Cyclepad software. So now we are going to go to software. So this is a Cyclepad software. Just double click it, give the name Reheat Rankine cycle, select open cycle and click OK. Now if you see over here, for point number 4 we have two data, 40 degrees Celsius temperature and dryness fraction is 0.85. So we are going to give properties of point number 4 first. So before we begin, we will first draw the setup. So we'll start selecting the components. This one is heater, so this will be boiler. Then we have a HP turbine, So this is a turbine. Then we have again reheating, means we'll select boiler. I'll rotate this, right click, rotate clockwise 90°. Then after the reheater we again have LP turbine, so I'll select turbine, left click and place the turbine over here, again left click. Then next we have condenser, that is cooler, and after cooler we have a pump, so this is the pump. Now join all the points. So I'll start with the boiler, so I'll join this such that inlet of the HP turbine becomes point number 1. Now click analyze now. Now here we'll first give all the processes to different components. Like for turbine we'll select it works adiabatically, it works isentropically. Then reheater, it works isobarically. Then again we have LP turbine, assumption adiabatically, isentropically. Then cooler or condenser, it works isobarically. Then pump, it works isentropically and adiabatically. And the boiler, it operates at pressure equal to constant, so isobarically. Now for point number 4 we have two properties, that is temperature, dryness fraction. So we'll start with point number 4. I'll select point number 4, which is exit of LP turbine. So I'll click over here, I'll select substance as water, then phase, select a phase for S4. So gas is basically superheated zone, liquid is basically subcooled liquid, and saturated is basically from 0.5 to this point. It could be either saturated liquid, it could be wet steam, or it could be dry saturated steam. So I'll select saturated. Now what is the dryness fraction of point number 4? 0.85. So I'll select this, assume a value for quality 0.85. okay, and temperature of point 4 is 40 degrees Celsius. Click OK. Now since we have to find specific work output, I'll assume m dot value as 1. So assume m dot is 1 and click OK. Now I'll move to point number 3. So point number 3, temperature has been given, reheated at constant pressure to 400 degrees Celsius. So I'll select point 3 temperature as 400. So I'll select point 3. Here the temperature is, assume a value for T3, it will be 400 degrees Celsius. Okay. Now here you can see automatically the phase has been displayed, that is gas. And what is the pressure being shown over here? 2136 kilopascal. Okay, and we have got approximately from Mollier diagram as 20 bar. Now next is point number 2. Now point number 2 is on saturated vapor curve. So here the dryness fraction is 1. So I'll select point number 2, phase, select a phase, it will be saturated, and dryness fraction, that is quality, will be 1. Okay. Now point number 1, the temperature is 500, so I'll select S1 point. The temperature of this point is 500 degrees Celsius. Click OK. So now it is showing that point number 1 is gas, so it is superheated steam, and the pressure which we got using theoretical method was approximately 150 bar, and here also we have got 15494 kilopascal. Now we'll consider point number 5. Point number 5 is on saturated liquid curve where dryness fraction is 0. So for point number 5, select a phase, it will be saturated, and quality, assume value, quality will be 0. Click OK. Now we'll confirm all the values which we have got of enthalpy. So if you consider H1, so before entry to the HP turbine, this is H1 before entry to HP turbine. So this value is 3298 kilojoule per kg. Here we got 3310. This is due to manual error while using Mollier diagram. So this value by the software will be more accurate. Then H2 value, here you see it is 2800 kilojoule per kg. Here also we got same value, H2 2800 kilojoule per kg. So H2 value is matching as it is. Here also we have H2 as 2800 kilojoule per kg. Then H3 value is 3245 kilojoule per kg. Here we have 3250 kilojoule per kg. So here you can see we have error of 5 kilojoule per kg using manual method. Then H4 is 2212 kilojoule per kg, whereas here we have 2220 kilojoule per kg. Now H5 value, so H5 value we have 167.5 kilojoule per kg. Here also we have 167.5 kilojoule per kg. And H6 value we have 183.1 kilojoule per kg. Here we have 182.61 kilojoule per kg. Now I'll go to cycle properties. Now this cycle is power producing cycle, so modeled as, I'll select heat engine. Heat engine is power producing device. Rankine cycle is also power producing device, so I'll select cycle is a heat engine. Now if you consider the value of turbine work, we have 1540 kilojoule per kg. Here we have power out as 1531. Okay, now the units are different over here because here we had considered mass as 1 kg, but here we have considered mass flow rate as 1 kg per second. So here we got kilojoule per kg and here we are getting kilojoule per second. Okay, but if you forget about the unit part, just see the values. We have 1540 WT and here I have 1531. So around we have error of 9 units. Then if you consider power in, that is pump work, here it is showing negative. We know work is done on the system, so that is negative. Here we are neglecting that negative sign. So here the pump work is 15.58 and here the pump work is 15.51. Now if you consider the efficiency, thermal efficiency, the software, Cyclepad software is giving 42.56%, whereas over here we are getting 43.04%. Now why is this? Because here when we are considering WNet, in the question it was given neglect pump work. So here I have neglected the pump work. So that is why here we are getting higher value of thermal efficiency. Now this is it. Here you can see heat supplied, Q dot in is there. Then heat rejected in condenser, that is also given over here. Now we can also see the TH diagram for the cycle. Here I have shown HS diagram. So if I go to cycle TH diagram, left click on this, so we'll get the reheat Rankine cycle TH diagram. So this is point 1. 1 to 2 is what? 1 to 2 is isentropic expansion in HP turbine. 2 to 3 is constant pressure heat addition in reheater. 3 to 4 is isentropic expansion in LP turbine. 4 to 5 is constant pressure heat rejection in condenser, and 5 to 6 there is isentropic pumping action. So with this we have completed the problem on reheat Rankine cycle using Cyclepad software.